Hello again everyone, welcome back to ptet.chemistry channel. So in this lecture tutorial video, lectorial, I'll continue on this topic 14 on atoms, elements and compounds. In the other lectorial, we cover the differences between elements, compounds, molecules as well as mixtures. And in this tutorial video, I'll go through methods of purification or separation techniques as it was called in many textbooks as well. Okay, so there has been a little bit of change in the syllabus content, and there'll also be a bit of change in how I cover it in this particular lecture tutorial. So in this lecture tutorial, I'll specifically cover this lesson objective. That's to do with definitions. So these are definitions, which mean that questions can ask you to define or state what you meant by a solvent, a solute, as well as a solution. All right. So each of these has a particular definition that candidates or students, meaning you guys as the viewers, the subscribers, you need to be able to define them as well as apply them when you write a longer extended answers in structured questions, right? Going on from there, I will not jump straight to filtration and crystallization. Instead, I'll decide to actually go through chromatography first, as well as interpreting simple chromatography. So this particular tutorial video will focus on this 14.1.2, 14.1.3, as well as 14.1.4. Alright, so essentially these are part of paper chromatography, and in this tutorial video I'll just particularly focus on chromatography because it seems that the Combined Science 5129 curriculum, they are very keen, they are very interested on asking questions involving chromatography, whereas filtration and crystallization and distillations, it seems that there is lesser that they could ask, but there's a lot more they could ask on chromatography. That is why it's a lot more popular. Alright, without further ado, let's get started with a little bit of definitions. So definitions are the most fundamental basic things that you all should be able to do because that is particularly stated in the syllabus. So a solute is just a substance that dissolves in the solvent, which is whatever it says here, a substance that dissolves in a solvent or a substance that is dissolved in a solvent. So each of these is a particular definition. So it seems like a rounded argument, but these are technical terms and therefore they are used as such. Alright. So solvent is just a substance that dissolves a solute. Alright. And a solution is a mixture because it consists of one or more solutes dissolved in a solvent. I'll give you an example. For example, if we have salt plus water, then we will get salt water solution. So that salt water is what we call a solution. The salt is the solid and therefore is the solute because I dissolve it in the solvent in order to give me a salt water solution. Alright, so question can ask, identify the solute, solvent and solution, and you need to be able to understand the definition in order to be able to break down exactly what is going on. Alright, this is just example. You could also, of course, have the other example being sugar. Okay, so sugar dissolved in water as well. So sugar plus water, they can give you a syrup. So you know what a syrup is, right? So very sticky, concentrated sugar in solution. So in that case, we have a syrup solution. And then the sugar is the solute because I dissolved the sugar in the water. So there's my solvent. Of course, it's not just solid that dissolve in the water. You could also think about, I don't know, the other one I could be thinking about is like coloring. Okay, so let's say blue coloring, but I'm using a pink color that doesn't matter. So like you can add a blue coloring to water and then you get a blue solution. So that thing, the blue solution itself, the solution is a mixture because it consists of the coloring dissolved in the water. So it's a mixture of one or more substances in the of the solute dissolved in a solvent. This is still the solvent, and then the blue coloring in this case is the solute. So the idea of me showing you these three different examples is to familiarize you with the use of these terminologies in the context of the kind of things that you are familiar with. All right. So solute dissolve in solvent to give you solution. Solute can be solid or it can be a liquid, as is the case with blue coloring, which sometimes colorings they come as solid, then it doesn't matter. Sometimes they come in liquid, already dissolved in some water, so you could just add more water to dilute it further to make it less concentrated. This is just a table on a general guideline on what is being separated from what. Like I said, I'm not going to talk through filtration in detail in the rest of the technique. I'll focus on chromatography. So I'll revisit some of these in the next part of these lecture tutorials where I focus more on the other techniques. But basically filtration is just used to separate solid from liquid, and evaporation and crystallization are pretty similar, except that crystallization is slower method, and you will get crystals. You get crystals in the end as product, and the crystals will always be purer than the evaporation technique, because crystallization is well, the crystals would be better than the solid there, and when you do evaporation, that could also mean they evaporate to dryness. When you evaporate to dryness, you could get a bit of impurities among the solid, whereas crystallizations will produce only pure crystals, because only pure substances crystallize out. Okay, so when you have impure substances, it's much harder for the thing to crystallize out. Simple distillation and fractional distillation are pretty similar, but fractional distillations, they need to have very different boiling point. They need to have very different boiling point. As you know, boiling point is to do with change of state, the temperature at which you go from liquid to gases, from the states of matter topic in the last chapter. In the last topic or last chapter. And simple distillation is what you typically do in the lab. That's just basically to separate a solution, which is a mixture of two or more solvents. And again, the solvents must have different boiling point. So the idea really is to do with different boiling point for distillation, because it involves boiling or evaporating. In fact, it's boiling rather than evaporating. It involves boiling the whole thing together, and then the thing with the lower boiling point will be distilled first. I'll focus on paper chromatography in this particular lecture tutorial. Paper chromatography, from the name suggests that it uses paper. The paper that we use is typically filter paper, alright? At least in our secondary level lab, we use filter paper. So chromatography, we separate out different substances from a solution, okay? And the principle is different solubility. That is the most important thing. The different solubilities of the substances, or what we say the solute, in the solution. So chromatography works because the different substances have different solubilities in the substances. Different solubilities in the solution, whereas distillation is to do with different boiling point. Filtration works because one thing is not soluble, the other thing is soluble, so you can filter them, you can separate them out. So I'll leave all of these and cover in the next lecture tutorial. Jumping straight to paper chromatography. So as I mentioned, we use them to separate our mixtures based on the difference in solubility of its component. Component in this case refer to the substances present in the solution mixture, or we can say the solutes in the particular mixture, but it's actually not to do with the difference of solubility in that solvent, in that solution, okay, but it's in that particular solvent. So you could be dissolving the stuff in water, but we are talking about the solubility of that substances in that particular solvent. All right, so this is an example of a chromatogram. So in this chromatogram, we will only use pencil. We only use pencil, not a color pencil, the graphite pencil, the one that has darker, well, the one which is not colored essentially. Okay, so we only use pencil to draw the lines. What lines am I talking about? These lines refer to this as well as where the solvent ends. Look at what happened here. So essentially what happens then is when you put this inside a container that has the solvent has to be below the line. The solvent, oh, I better put the arrow further in. The solvent must not get above the starting line. So this starting line is drawn with pencil, and then at the start of the experiments you will have a particular dot there, so you have them dotted there, and then this thing dotted here. All right, and what happened then is the solvent, this thing have solvent inside it. Depending on the solubility of A and B, as well as these two things present in this mixture, in this solvent, they will travel at a particular distance up the filter paper. All right, so they're traveling against gravity, so it's always going to be slow, but the more soluble the component or the solute in this solvent, the faster they will move, meaning the further they will move in the given period of time, they will move further. So for example, if I compare A and B, this is a pure substance because there's only one dot that's separate out. This is a pure substance because there's no other dots that has been separated out. It's separate only into component B, which is just one particular dot. This is a mixture. This is a mixture because you have two dots separate into two or more components, meaning to say the original dot that you put here, it has two substances here. They have separated out, they have traveled at a different distance up the filter paper as the chromatogram shows you. Okay, and therefore we can say that this travel further, so this is more soluble in the solvent compared to this. B has traveled further than A, okay, and B is more soluble in the solvent than A. So what information can you get from all of these, right? B travel further than A, B is more soluble in the solvent, which I don't know what it is yet, okay, than A. This particular dot is more soluble than this particular solute or this particular substance, all right? So this is a mixture. Does it contain A or B? It moved up here. You can see this is the pure substance, this is the mixture. This thing has exactly the same distance move as for component A, which is pure. So I can say that by looking at this and this, so the mixture has component A. Does the mixture have component B? Well, let's have a look. B would have a value, would have moved up at this particular distance, but there's nothing that has moved up this particular distance because they are all spot at the same starting point. They are all put together with the starting line just above the solvent, and there's nothing there, okay, meaning to say this is not there, this is not there, there is no component B in this mixture. So the mixture has no component B, has no component B. So these are the kind of information that you can get just by looking at this picture alone, right? But they will move up and up and up and up, okay, provided you don't take this filter paper out. They will move beyond the length of the filter paper. So what you must do towards the end is you must take out the filter paper before the solvent wets the whole filter paper to the very end. So that's why we take it out before the solvent, which you can see when the filter paper is wet. We take it out before they reach the very top of it. Then we use a pencil again to make a mark there, and you can use a ruler to draw a line, and that is where we say the solvent ends, because that is where the solvent stops moving until when we take out the filter paper, okay, to give us the chromatogram. All right, so we have to draw it with pencil as well, and that's because we use pencil because pencil made out of graphite is a pure substance. All right, it's a pure substance. We don't use ink because ink is a mixture. Ink is a mixture, it's something dissolved in water, and ink is a mixture. If you use ink to draw the lines, the ink itself will separate out. together with your substance. So you're trying to separate what you wanted, okay, but then your ink, which is a mixture, will also separate out. So it's not a very good technique if you use ink. If you use a pure substance which doesn't separate out, graphite, because graphite is typically insoluble in most solvent. There's this thing called retention factor. You don't have to worry too much about what it's called, but the idea is that every substance, depending on its solubility in the solvent, they will move a particular distance from the starting line. How far they have moved from the starting line to the top, you use a ruler, and then you measure the height. Okay, so that height, that is the distance moved by the component from the starting line. Different component will move a different distance from the starting line, as you see there. Okay, I'll use blue again because that is very clearly component A, and I'll use a different color because that is very clearly a different component. So you can use ruler to measure exactly how far they have moved. Okay, so I'm doing this on my screen, but everything is to do with ratio. So if you have this on paper, you should do it on your very own paper, and you should get the same ratio. All right, the distance moved by solvent from the starting line is basically this thing here. So from the starting point, okay, not where the solvent dips, okay, in, okay, so not this brown line, but this black line where you have the starting line. So from the starting line to the solvent ending line, that is the denominator, that is the distance moved by the solvent from the starting line to the ending line. So I should have added to the ending line. Okay, as I mentioned just now, so how it works really is to do with the solubility in a particular solvent. So if it is more soluble in that solvent, it travels further up, and therefore since it moves further, and this distance is the same for the whole chromatogram, okay, so if it travels further, the RF value will be bigger because the bottom is a constant value. The one up there will have a bigger distance, and therefore RF will be higher. So how do we know what is what? So I can say that they are the same substance because the RF value for this thing is equal to the RF value for component A. So that's how I know this mixture contains component A, but it does not contain component B because the RF value for this dot does not correspond or does not equal to the RF value of this component B or component A, unless it's this one, okay? So some of the conclusion we can make is that component A is pure, so is component B. It doesn't separate out into other substances. This is a mixture. It has component A, which has RF value being equal, but this thing is an unknown component. It's not A, it's not B, okay? So if a spot is colorless, okay, so these things could be colored, then you could see. But how do you know when something is colorless, then you cannot see? If you have something that separate out into something which is colorless, you might need something called a locating agent. So what does a locating agent do? It makes the spot colored. It makes the spots, okay? So if the spots are colorless, it doesn't have color, you don't see it. Just like water, you don't see water. But if you put a bit of coloring onto it, you can see the water. So that's why we need a locating agent to make something colorless visible, and that is very obvious in order for you to know and see it. Only then you can work out the RF. If you can't see it, how can you work out the RF to begin with? Okay, so that's it really on that particular concept. I'll just jump straight onto the checkpoint questions.